great. So good afternoon, everyone, and hello and welcome to this Institute Molecular Science and Engineering Highlight Lecture, which today will be about antimicrobial surfaces and fighting the battle of antimicrobial resistance, presented by our guest, Melina Gerdts, who is the CEO and co-founder of CuConcepts. My name is Gérald Arumomus. I'm senior lecturer in Department of Life Sciences, doing mainly microbiology. And of course, I am also the Institute Molecular Science and Engineering Challenge Champion for Antimicrobial Surfaces, which, just to remind you, we have published in March 2020 a briefing paper about this topic, and you are highly encouraged to have a look at this, which is on the IMSE website, and also the different strategies we are using to tackle antimicrobial resistance. Few words about IMSE. IMSE is one of the global institutes which try to foster collaboration within academia, but also beyond academia. Just to remind also that this is a hybrid event, so thank you for the people who made it today, despite the tube strike, to join in person, but also the one who are listening to us online, which I hope you will have a great experience this afternoon with us. Just for the one joining online, remember that you can still post a Q&A session, but that, or your question, but that should be using the Q&A function in the, not in the chat, but in the appropriate place. If you have any issues regarding the posting your question or technical issues, please do send an email to IMSE Imperial and we will quickly address this query. Then I will now hand over and introduce Melina Gerdts, our speaker this afternoon. So as I said, Melina is the Chief Executive Officer of and co-founder of CuConcepts, a Berlin-based biotech startup battling the spread of infectious disease. Basically, Melina has lived in different countries, which bring her to this awareness of the spread of superbugs and how to address those superbugs using new and method like or approaches like antimicrobial surfaces. And particularly, Melina has more in addition to some scientific background, more a business background and extensive management and consultancy expertise in polymer processing, chemicals, green material, and agriculture. So she is leading CuConcepts in its mission is to have safer, healthier world by providing solution and of course pandemic preparedness. Thank you very much for joining us in person today, and we look forward for your talk.
Thank you, Gerald, for the introduction, and also for inviting me to come speak here today. It's an honor to take part of the Highlight Lecture Series. So as Gerald has already mentioned, I am CEO and co-founder of CuConcepts. We are a startup developing antimicrobial materials to battle the spread of infectious diseases. So today I'm going to talk about antimicrobial resistance. The first half of the lecture is going to be dedicated to this topic, what it is, why it's important to know about it, and what the implications are of it if it continues to go unchecked. And the second half of the lecture is then going to be dedicated to antimicrobial surfaces, as well as what CuConcepts is doing in this field. So before I start, I'd like to share a story of a friend of mine who is a doctor in Germany and Italy. And she told me about an experience she had that really defined her career. So around 8 years ago or so, she was in the middle of her medical degree, and on a Sunday afternoon, her supervising doctor contacted her and said, "We have a very big emergency in our ICU at the moment, because we have a patient that has been tested for multi-drug resistant infection. And we need to discuss this as soon as possible." So the next day, Monday morning, they met and tried to consult on what to do. The antibiogram showed that the patient was unfortunately resistant to all antibiotics that exist today. So what happened here? They obviously tried everything they could to save this patient. However, later that week, the patient passed away. Now, this is something that is happening on a big scale. This is just one of the stories, and something that is quite worrying for the healthcare community is the rate at which antimicrobial resistance is actually spreading So you can see here, these are some antibiograms. On the left, this was a patient in Rome. You can see here, they were susceptible only to 4 antibiotics that worked. They were able to save this patient. On the right, you can see an antibiogram done on Pseudomonas, which was pan-resistant, meaning that none of the antibiotics were working, not even colistin, which is considered to be a last resort antibiotic. And here is an antibiogram that actually went viral on Twitter. This was by a doctor in Germany, Dr. Annette Hedix, who posted this antibiogram. And you can see here that colistin was the only susceptible antibiotic to which the infection was susceptible. So this is just a snapshot of what is going on a micro scale. So what is antimicrobial resistance? It essentially occurs when microbes grow resistant to a medicine as a result of having developed the ability to defeat the drugs. This happens through gene mutation. So these are often called superbugs, which is in a way a cute name for something that is extremely lethal and not to be underestimated. So how does AMR spread? Once there is a gene mutation, it can either spread from a parent cell to its offspring by a vertical transmission of the genes, or through horizontal transmission, which is between bacteria. Now, in the last 40 years, there have not been any new scientific discoveries with regards to technologies with which antibiotics can be developed. So today, all antibiotics are actually based on scientific discoveries done in the golden age of antibiotics, which was when Alexander Fleming first discovered penicillin in the 1920s until the 1980s. Novel antibiotics are actually the most underserved area within drug discovery and development pipelines. This is owed to a high risk in investing in R&D in this field because there is also a low profitability associated with this segment, and also a lack of financial incentives from public funding sources and a regulatory point of view. So the World Health Organization published a list of priority pathogens in 2017 in an effort to support the R&D into new antibiotic technologies. It comprises 12 families of bacteria. And if you can see on the right here, the critical ones are all resistant to carbapenem antibiotics, which are a form of last resort antibiotics being used. These 3 are also part of the escape list. The escape pathogens are the most serious group of multi-drug resistant bacteria, as they pose a particular threat in the healthcare environment in form of nosocomial infections, which is another word for healthcare associated infections. So infections that you contract during your stay in a healthcare environment. So you can see here that E. coli, for example, or Staphylococcus aureus cause infections such as a urinary tract infection or pneumonia. And these are actually now lethal in certain cases. So what are the drivers of antibiotic or antimicrobial resistance? As discussed previously, the resistance is a result of gene mutations. Now this happens when there is a high pressure environment that drives the selection process. And one of the major factors is the overusage and misuse of antibiotics. So overusage, what does that mean? Antibiotics are often used as a prophylactic in hospitals. So just in case you might contract a bacterial infection, they give this to you in advance, which unfortunately drives the resistance. Or they implement it during viral infections, which is pointless as antibiotics have absolutely no effect on viruses. And also studies have shown that people generally like to take antibiotics for a couple of days until they feel better, and then they stop after 4 or 5 days and do not actually take the antibiotics for the recommended period of time. This means that during the 4 or 5 days that antibiotics were taken, the, let's say, weaker pathogens are eliminated, but the stronger ones survive, driving the resistance. We also have antibiotics being used as a growth promoter in livestock management. A side effect of antibiotics in animals is that it fattens them up. So this is a nice way to increase the output for industrial farms. It's also being implemented as a prophylaxis just to avoid a major outbreak of disease among cattle or chickens, for example. And something that is also worrying is that it can cause cross resistance, which means that antibiotics being implemented for animal health are causing resistance also within human medicine. Then there is the environmental pollution of AMR, where we essentially have the discharge of non-metabolized antibiotics that enter the environment through faulty wastewater management, through piping. And you also have pharmaceutical industry pollution, which is, for example, one of the main drivers of the AMR crisis in India today. Unfortunately, the recent COVID-19 pandemic is also a major driver, as there was an increase in antibiotics that were prescribed to patients that were in hospital due to COVID, also as a way to either prophylactically avoid a healthcare associated infection or as a way to actually counter one that has already been contracted. And there's also a problem of misdiagnosis of symptoms, as it is difficult to tell the difference between a viral or a bacterial infection, for example, if you think about pneumonia. So in a way, climate change is also a further driver, to the fact that there is an increase of zoonotic diseases that are triggering epidemics and a recent pandemic. Zoonotic diseases are diseases that cross over from animals to humans. Now, these future epidemics and epidemics that are already happening will further drive the overconsumption of antibiotics. And then you have the general trend of globalization, where you have access to very cheap travel routes, you have global logistics chains, and you also have international food chains, which are essentially a very convenient way for microbes to spread across the world. So the global transmission of antimicrobial resistant microbes is a cross-sectoral crisis. So we look here at some factors that influence this, as discussed: no access to clean water, faulty sewage systems, variations in the standards of healthcare infection controls, inadequate provision of antimicrobials, especially in middle or low income countries, farming systems that don't have a rigid regulation in place with regards to the use of antibiotics in livestock management, as well as high population densities, making it easier for gene transmission. So what does this actually mean in numbers? AMR is today already identified as a leading cause of death globally. It doubles a patient's chances to develop a serious health issue when located in a healthcare environment, and it triples the chance of mortality. It also prevents the effective treatment of infectious diseases and complicates medical treatments where antibiotics are actually used on a routine basis. So any kind of surgery, chemotherapy, stem cell therapy, etc. Today, or in 2019, 1.3 almost million people died with a directly related to an AMR infection. That is more than HIV and malaria deaths in 2019. So taking a look at the numbers of deaths across the regions, you can see, of course, Europe and the US being impacted, but more scaringly, India has 60,000 AMR deaths of newborn children per year. And then you have the sub-Saharan African continent, where you have an estimate of 255,000. However, it is speculated to be much higher. What does this mean in terms of costs to the healthcare system and economies? You have very high associated healthcare costs and productivity loss. So approximately 75% of infections with drug-resistant bacteria in the European Union area are associated with infections that are contracted in a healthcare environment. So in the EU, AMR is estimated to cause around 1.5 billion euros in additional healthcare costs and productivity losses. You can see below a table which shows the effects of healthcare associated infections. So not necessarily with a multi-drug resistant infection, but overall healthcare associated infections. This is owed to an increase in drugs that have to be implemented and expensive treatments as an alternative to antibiotics, prolonged hospital stays, higher readmission rates, increased cost of testing and diagnoses of these infections, cancellations and postponements of elective surgeries, as well as isolations and closures of ICUs. So it's projected that AMR will cause 10 million deaths every year in the next, or in 30 years. You can take a look here at the mortality rates compared to other common causes of death, like for example, cancer, diabetes, road traffic accidents. So this will be the leading cause of death if this continues to be unchecked. It will send us back to, well, the dark ages of medicine, which essentially would be the post-antibiotic era. And here it would be important to obviously find some other solutions to contribute to the fight, not just antibiotics. So there are strategies in place to counter AMR. There are organizations such as the World Health Organization, the FAO, European Commission, CDC, etc., that have developed action plans on both a national and international level, such as the One Health approach. And they have sort of 5 key underlying strategies. So the first one is improving the prevention of infectious diseases in the first place. That is also going to be the focus of the remaining lecture. You also have extending the implementation of antibiotics stewardship, so essentially developing programs for healthcare professionals to responsibly prescribe antibiotics. Then, of course, developing and applying improved molecular microbiological diagnostics to speed up the process of actually diagnosing a multi-drug resistant infection, developing new classes of antibiotics, but also developing alternative therapeutic approaches such as phage therapy. So, as also discussed in the brief paper by Gerald and his colleagues, the transmission of microbial pathogens can actually happen through the touch of contaminated surfaces. This is significant and a concerning problem for health authorities. So you have biofilms that are essentially a cluster of bacteria protected by a kind of slime that attach to surfaces, and they have the ability to protect the microbes from attack from antibiotics and biocides. Now, the problem is if these biofilms are attaching themselves to surfaces that are frequently touched, or if they're attaching themselves to medical devices being used in procedures, they can result in infections such as urinary tract infections, infected hip joints, but also infections of the water stream with Legionella. So, whilst direct person-to-person contact is obviously important in the transmission of pathogens, the contamination from common touch surfaces, also called fomites, also play a significant role. So you can see here an overview of 3 pathogens that were tested for in a few different healthcare environments, different environments. So we have MRSA and VRE, which were found in hospitals and nursing homes. And these were found on common objects such as an ambulance stretcher, personal protection equipment from the staff, lab coats, as well as in general objects that come into contact with patients. And salmonella, which is obviously a foodborne disease, has been found in various food processing facilities, especially on surfaces and machinery where food is being processed, as well as food packaging. So how long can pathogens actually survive on different surfaces? They can be controlled, obviously, by cleaning and decontamination practices with disinfection. However, these practices don't always eliminate all of the risk. So a study was conducted across 27 ICUs, which found that basic cleaning protocols only resulted in the disinfection of around half of all of the high-touch surfaces. If you take a look here, you can see some of the escape bacteria, such as E. coli, can last for 36 days on a surface. You have Staphylococcus aureus can last over 90 days. In the second table below, you can see viral pathogens. So the recent SARS-CoV-2 virus, which causes COVID-19, can stay on a surface for up to 3 weeks. So what else can be done to counter this problem? Antimicrobial surfaces can contribute to infection outbreak control because they have the potential to reduce the contamination as well as eliminate biofilm formation, hereby reducing healthcare associated infections. Here are an overview of 3 types of mechanisms. There are more, but these are 3 major ones. So on the left, you can see anti-adhesive surfaces, which essentially reduce the adhesion of microbes to a surface so they can't actually attach. On the right, you can see antimicrobial surface patterns. So these are essentially surfaces designed on a nanoscale that have structures that can pierce through cell membranes, for example, and hereby eliminate the actual pathogen. And then in the middle, we have the third type, which is an inbuilt slow-release antimicrobial agent that can be found in a material or in a surface, which releases ions, and this process eliminates the bacteria that come into contact with the surface. So we're going to focus on copper for now. Copper is actually a very ancient, efficient antimicrobial material. It was used back in the time of the ancient Egyptians, who stored water in copper buckets to sterilize it. They also laced treatments for wounds with copper. They mixed copper shavings with honey and cow fat to treat ulcers. And a study was done in Paris after it was discovered that workers of a copper mine were actually shown to be immune to the cholera epidemic. Now, copper has a very broad range of antimicrobial efficacy. It is antibacterial, antiviral, and antifungal, making it extremely efficient. It also works independently of the environment, meaning that it doesn't necessarily need humidity to activate the release of ions. And it also works in humid environments, though. And it does eliminate 99.9% of all pathogens on a surface within a short period of time. Of course, depending on which type of microbe, these times differ. So a lot of studies have been conducted on the effect of copper and also how it can reduce healthcare associated infections, actually by around 50% in healthcare settings. Hospital beds that were covered with copper or copper alloys were found to have a reduction of 95% of the bacteria compared to beds that didn't have this equipment. And as I mentioned previously, basic cleaning protocols don't always guarantee the disinfection of a high-touch surface. And the antimicrobial effect of copper, however, is continuous, which makes it a great complementary tool and almost a passive tool that is active in the background. One other study actually found that on solid copper materials, the horizontal gene transmission is actually limited among bacteria, which of course is extremely relevant for reducing the spread of multi-drug resistant pathogens. So you can see here some of the time it took, the so-called contact killing effect that copper has on pathogens. You can see the SARS-CoV-2 virus on the very top was eliminated within 4 hours. You can take a look at some of the escape bacteria such as MRSA, eliminated within 3 hours, or Acinetobacter within also 3 hours, and some of them even less than 5 minutes. Here you can see a study that was conducted with the influenza A virus on comparing it on stainless steel as well as on copper. So on the top you can see the virus population after 6 hours, and on the bottom you can see on the right after 6 hours on copper. There was only 500 virus particles left, while on stainless steel after 24 hours there was still 500,000 virus particles left. Here was a study also conducted on copper comparing, on the COVID-19 virus, comparing it to the survival on cardboard, on stainless steel, plastic. And you can see here that copper had the most efficient elimination time, which was 4 hours. So recently we were at a trade fair and we held a competition for the visitors who has the most contaminated phone case. This was meant to attract the attention, but also raise awareness. Now we took swab samples from 80 visitors at the fair over a period of 2 days. And we used an ATP meter device to test the level of microbe contamination on the surface of the phones, so the front and the back. Now, on the left, you can see a spectrum, and the ATP meter device essentially shows you some standardized values. So a value of 10 means it's pretty sterile. So a surgical tweezer would not be allowed to have a value that exceeds 10. If you have a restaurant, the result cannot exceed 50, or else you will not receive the sanitary certification allowing you to actually operate a restaurant. Now, at the end of each day, one of my colleagues went to the male bathroom in this trade fair and took a swab from the toilet seat as well as inside the toilet, and the value reached 653. Now, let's take a look at the average values of the phones that we tested. So on average, the value was at over 1,000. This is taking into account both adults and school children. Now, interestingly enough, we had a higher average for male teenage boys. They actually beat the overall average. I'm just going to leave that number there. And teenage girls, surprisingly, were a bit less. Now, one of the dirtiest objects we've actually identified was a separator, the goods separator in a supermarket. So, you know, when you're at the conveyor belt about to pay and you place that little triangular plastic piece to separate your goods from someone else's, well, that had a value of over 3,000, which is a bit worrying considering you're placing this in the middle of your groceries. And we had an anomalous phone value at this trade fair. We redid this test 3 times just to be sure. We have no idea what he did with his phone. He did proceed to throw away the phone case after he did this test with us. And the winner of this competition was supposed to receive a CuCase, which was actually one of our first products. It was an antimicrobial phone case, which, by the way, never exceeded a value of 90. And we never clean it. And yeah, surprisingly, this winner actually never came back to take his prize. So CuConcepts, what are we doing? We are battling the spread of harmful microbes via contaminated surfaces. We're doing this with an additive that is based on copper salts and that can be integrated into materials, especially polymers. So here it's integrated into the polymer matrix during the polymerization process. And once incorporated into a master batch, it can be further processed via injection molding, for example, or extrusion or blow molding, also 3D printing. You can see on the right some of the materials that we have successfully tested with this additive. So for textiles, these would be polymer threads that you can weave into a textile. And the final part containing CuCare inside will have the antimicrobial properties, meaning that on a surface of a material that has this integrated, 99.9% of microbes will be eliminated. The technology does not migrate to the surface, so it actually remains within the material, which is important for applications that come into contact with food and water. And it's actually the copper ions that come into contact with the surface and the microbes that are on it. So you can see here, this is the current theory of how our technology is eliminating microbes. This is bacteria specifically. So you have copper ions that are released from within the material, they travel to the surface, and they cause the formation of reactive oxygen species, which induce stress on the cell membrane, causing it eventually to rupture. So the cytoplasm leaks, and then the nucleic acids, so DNA and RNA, where the genes are located, are degraded. So this is important because this results in the destruction of the cell, and it mitigates the risk of the bacteria regrowing or even mutating. Here we have some tests just to show. This was conducted on polyethylene, actually, where you see a log3 or log4 reduction, which essentially means that 99.9 or 99.99% of the microbes were eliminated within 24 hours. This is part of a test you do to attain the ISO 22196, which is the certification you need to make antimicrobial claims. You can see here, this was actually a test conducted on a 3D printing filament that we developed with a company in Italy. You can see on the left the difference, and this received a log reduction of over 2, which is 99.9% of reduction within 24 hours. We also had it tested with the COVID-19 virus, and you can see here that the highest concentration eliminated the virus within 1 hour. So here's another case study that we conducted in a town hall in a town in Bavaria, where we equipped door handles with an adhesive film that contained our additive, which was a polyethylene layer and then an adhesive on the other side. And we covered certain door handles of exits and bathrooms with this adhesive film. And we instructed the cleaning team to not touch these surfaces for the next 12 weeks. Then we identified some control surfaces, which are regularly being cleaned. So once per day. And we went once per week to actually test the surfaces and compare. So this was right after, a few hours after the disinfection happened. This was always around 2 p.m. And you can see here that on the bottom, the two, the yellow and the blue data, they show, let's say, a level of contamination of around, let's say, below 100 constantly, continuously, even though it was not cleaned at all within the 12 weeks. And then on top, you can see a bit of a more erratic behavior, which is owed to the fact that a door handle that is being cleaned is only clean as long as the next person touches it and then potentially contaminates it. So apart from healthcare environments, where else can antimicrobial surfaces be useful? We're having some projects with a public transport company who was interested in implementing this in their high-touch areas, in packaging, 3D printing for prototypes that are being developed, in the sharing economy. So actually a lot of automotive manufacturers are now interested in antimicrobial surfaces on dashboards and steering wheels, as well as the ventilators. Of course, piping, extremely important application because this can potentially mitigate the growth of contaminants like Legionella. Industrial applications such as in construction, where you can reduce the growth of mold. And of course, on various consumer goods. So for example, a water bottle, which after a while develops a certain smell if you don't clean it correctly, which is owed to the bacteria that grow on it. And the additive eliminates the bacteria, herewith also eliminating the odor. Here are a selection of the active case studies that we are doing with companies at the moment. So the first one you can see, this is a manufacturer of beds used in healthcare environments, and they have a synthetic leather made of PVC, which they have now, or they want to make antimicrobial. So here we've managed to develop a material that works well. And this will reduce drastically in a passive way the contamination on the surface of these beds. We also have a public transport company who's interested in implementing this for high-touch surfaces like handrails, but also potentially the textile of the seats. We're also working with a company who makes packaging for healthcare devices. So here a differentiation factor. Underwater cables that have the problem of the growth of mold. So this can be mitigated. We also have a company that just launched the CuMake, which is a 3D printing filament based on PLA. So a bioplastic. This was actually intended at first for a project they did with a museum where they wanted blind people to be able to also see the art. So they made sculptures 3D printed with this material. So it was in a haptic way possible for the blind visitors to also see the art. And then another company who's interested in implementing this in dental care products. Now we have also something quite exciting in the pipeline, which has nothing to do with copper actually. This is a nature-inspired technology, or let's say plant-inspired technology that will have selective properties. So the idea here is that the antimicrobial effect will not happen for 99% of all microbes, but instead it will selectively target a type of bacteria strain or a virus. And this is very useful in certain applications where you actually have benign bacteria that you do not want to eliminate. So for example, applications within the human body, hip joints, for example, but also in the dental region, so dental prostheses that get infected often. Here we do not have the issue of not being able to comply with the biocompatibility norms, so making it very interesting for the medical environment. And the idea is here to also integrate this into polymers, but it also opens the door for some new applications, basically as an enabling technology for industrial fermentation processes, as here the contamination of harmful microbes or fungi and bacteria can cause a lot of the output to be contaminated. And yes, this will be done all in Europe. So CuConcepts aims to develop a portfolio of antimicrobial technologies over the next 5 to 10 years. So copper-based, plant-based, but also modified surface structures on a nanoscale with new kinds of materials. Some of the challenges that companies face in this segment include, first and foremost, the lack of public awareness about this topic, requiring high efforts to actually educate the counterpart, as well as convincing partners or customers of something that they cannot actually see with their own eyes, as well as building a business case for companies to demonstrate the cost-saving effects, as this is usually one of the reasons why companies invest in novel technologies, because it improves their profitability. Now, on the other side, we also have a lot of high costs and timeframes associated with getting the relevant certifications and norms to be compliant. These processes are often very intransparent, highly bureaucratic. We have a tight regulatory framework, especially regarding the use of biocidal active substances in the European Union. So this is under the European Chemical Agency. They have the BPR, which is the Biocide Product Regulation, under which you have to be compliant. And this is also an extremely bureaucratic process with very high entry barriers. And also with regards to funding, the attention is diverted recently, or was diverted mainly to developments in the field of research to battle the COVID-19 pandemic or climate change. Now, these are also extremely important issues to tackle. However, AMR is just as important. Now, in conclusion, we do face a very real threat of having to survive a time where antibiotics are no longer going to be effective against infections, meaning that you could potentially die of a cut that gets infected. This crisis requires a multidisciplinary approach across all disciplines of science and a multisectoral approach, so the involvement of government bodies, regulatory frameworks, public funding institutions, the scientific community, healthcare professionals, but also the private R&D sector to actually tackle this issue, which is systemic. And reducing antibiotic consumption alone will not be insufficient to control AMR on a global scale, as the spread of the resistant bacteria and of the resistant genes is a dominant factor. So part of the infection prevention control measures can be antimicrobial surfaces, because they represent a complementary tool. They are a passive way to reduce antimicrobial survival, to eliminate pathogens that come into contact with the surface. And they can also reduce the risk of contracting infections in healthcare environments. So I think we can all agree that if you prevent contracting an infection in the first place, that is better for everyone, because then you will not have to deal with actually healing the infection. Thank you, everyone.
Thank you very much, Melina, for this very nice overview of the issues of antimicrobial resistance and how CuConcepts is approaching this approach, its problem, and particularly the very interesting part of the plant-based. Of course, this is promising avenue. So now I open the floor for questions. So if you're online, you can type your question in the Q&A, and we will read your question, and Melina will answer a question. And if you're in person, you will be given a microphone. Just raise your hand. You will have a microphone, and you can ask directly your question. I think we have one question in the Q&A.
I can read that out. What has been the most challenging experiences for you and CuConcepts with regards to bringing technology to the European market?
Yeah, good question, because that's actually, there's a few challenges. The biggest ones, I would say, are two. The first one being funding. So as any startup, funding is always an issue, but in an environment where you have, or in an industry where you have very long R&D cycles, and also high risk associated with this investment, it is quite difficult to attain funding, especially in the short run. On the other hand, the regulatory framework is also something that has proven to be the biggest challenge, because not only do we have to be compliant on an international scale in Europe, but also with a variety of certifications to be able to apply this technology safely in a variety of industries.
Hi, thanks for that. Just a question on like the nanostructured surfaces. Those are the nanopillars, nanospikes. How advanced have those become generally? How easy are they to use? Are they widely applicable? Because I can see, putting nanopowder surfaces is not necessarily an easy feat, but getting it on like three-dimensional shapes itself is going to, like, say, a scalpel handle is going to be a bit tricky. So yeah, anything like that, I'd be interested to hear.
Sure. So as far as I know, this field is mainly still under development. There haven't been any high scale, let's say, products that are implemented on a global scale. What is interesting is that this is closely related with biomimicry, because you have a lot of surfaces in nature, for example, the wing of the cicada, that actually have this structure in their wings. So this is a source of inspiration, let's say, to design the surfaces in this way on the nanoscale. Yeah, and so since we are also aiming to contribute to research in this field, this will happen a bit down the line, so I can't really talk about right now, but but as far as I know, it's not something that is being implemented on a major scale.
So I have one question. So you talk about incorporating copper salt into different polymer, like either plastic or others. So is the concentration of this salt varies according to the polymer you use, and how efficient it is and stable are these copper salt in the different solutions?
That's a good question. Thank you, Gerald. So actually, the concentration doesn't vary that much from polymer to polymer, but the sorry, can you ask the second part of the question?
So is there variability of efficacy between PVC copper and other materials, and particularly how effective it is? Because you presented like within 5 minutes, some bacteria, for example, can be killed with copper, but is that still valid for PVC-based polymer or PE polymer, for example?
So depending on the microbe type, the killing time varies a lot. So some happen within 5 minutes, others do take more than 24 hours, especially fungi. They're a bit more tricky with that regard. We do, in general, have recommendations of the concentration of the technology in the final part. So if you're in the, let's say, if it's an application in the healthcare segment, it should be around 1% of the final product. In other applications, it can also be at around 0.6%. So between 0.6 and 1% of concentration, depending on how efficient and how fast you need this effect to work.
Okay. Yeah, but what question is in chat?
Yep. So another question is, have you done a cost-benefit analysis of copper-based treatments compared to any other surface treatments?
That's actually something we're working on right now, as this is a key argument when discussing the, let's say, contribution to profitability for companies. And yeah, to be honest, no. So we have a few other materials that have this effect, like silver-based, for example, or zinc-based or titanium dioxide-based. But at the moment, we are still working on actually creating this cost-benefit analysis for our own technology, depending also on the application, because in a healthcare environment, this is going to be different. It's going to be a different effect. So, for example, if it's going to be about reducing the actual infection rates happening, and then you also have other applications, like in construction, for example, where you have a very different time frame you're working with, and you also have very different profit margins you're working with.
I have another, John.
Thank you. How are you going to deal with the color problem?
That's a good question. So color is actually one of the major points that could break your neck in that case, in that sense, because, for example, silver ion technology has the problem of discoloration. Copper does too. So the natural color of our additive technology mixed into a plastic is kind of like a minty green in a way. So kind of the color that copper has once it has oxidized. We are working together with companies that are specialized on polymer production. And here we have one specific partner with whom we've managed to actually cover the entire color range until almost a very clear white. So it's a white that has, let's say, a hue of mint.
I have one question regarding the plant-based, because it's a natural product. Have you considered the degradation of that product over time compared to copper, which is a transition metal and have obviously less degradation.
Sure. So the plan is to biosynthetically manufacture the compounds inspired by this plant. And this is something that is still under development. So we are trying to, to understand how to stabilize it in the long run. But also some of the applications will probably be more short-term than long-term for the plant-based one.
Great. If we don't have any more questions, so I would like to thank you very much, Melina, for this very nice presentation. Thank you for the attendees this afternoon in person, and of course, the one who has been attending the seminar online. And of course, for the one who are in person, we will have further discussion outside in the foyer around the coffees and teas. Thank you very much again, and looking forward for next step in the development of your startup company.
Thank you, Gerald. Thank you for having me. And thank you for your attention.